So I want to explain this beautiful article, Approximation Aware Dependency Parsing by Belief Propagation in 2015. This article, again by Jason Eisner. And there is another article that I will explain, this one that I will explain in future. It is also important. So everything is the same. Now our training is different. So we show how to train the fast dependency parser of Smith and Eisner for improved accuracy. But now it outputs the parse with maximum expected recall. You know, F1 score is recall. You use recall and precision to create F1 score. This is a different. This is related to that. So it outputs the parse with maximum expected recall. But for speed, this expectation is taken under a posterior distribution that is constructed only approximately using low-p belief propagation through structured factors. We show how to adjust the model parameters to compensate for the errors introduced by this approximation by following the gradient of actual loss on the training data. We find this gradient by backpropagation. By the way, backpropagation and belief propagation are the most important parts of artificial intelligence, because what we do in action, what our brains does in action. So our brain, for example, uses message passing. And so belief propagation and message passing are, backpropagation, it is in deep learning, you know that. Belief propagation, it is in classical probabilistic reasoning that you are familiar with Judea-Pearl in 1980s. And so we want to treat it very differentiable, just like backpropagation. So for me, they are the same thing. Of course, it is strange to say that, but if you write it down, you will notice that you see some connections between them. And there are a lot of articles, of course, to see the relationship between backpropagation and belief propagation, unifying them, making them differentiable, making them end-to-end. And so it's an interesting research area. So let's review our model, in our factor model graph in the previous lecture. As I said, between two nodes, two words, let's say, for example, between this word, and a root, there is a variable. If this variable is 1, then there is a pass between them. So this is the head and this is our modifier. Or you want to dependent. Another word for modifier is dependent. So head and modifier, let's say. And so in this way, you create your dependency graphs. So everything is simple. And you say, okay, so how are you dealing with those higher order constraints, higher order dependencies that you promised? Okay, I say, for example, this one is a factor which is a constraints for higher order. For example, this edge and this edge. There are 2 edges, or it could have multiple edges in some cases. And also this is our 3 constraints. So as I said, constraints are in the square, and just normal variables are in this circle. And so in previous lecture, you see that these are some of them are soft constraints, some of them hard constraints. And we model the potential functions using, again, like linear models is our friend. So theta is the parameter that machine should learn, and f of alpha is the features. And x is the assignment to the observed variables such as sentence, and it's part of speech tags. And we write the resulting probability distribution over parsers. What is the probability of y, a particular y given x? And because it's a parse, it's just a vector of 0 and 1 if that edge or binary things, if they are related or not. So this represents a parse. And so the loss could be, you say that if, for example, my gold edge says that there is an edge between two nodes, but your prediction says that they are not. So there is a conflict between the gold and what you have predicted. This is the normal loss that you always do. But now we are using a minimum-based risk decoding by saying that we calculate the probability because the belief propagation calculates them. So we fit it here and then we calculate the probabilities. So there is here is discussing that maximum posterior is different than minimum Bayes risk, and we know that. So minimum Bayes risk decoding, so our goal is this. So let's see how we do it. As we have done in the previous lectures, we do it by belief propagation. And in belief propagation, we use loopy belief propagation, computes approximations to the variable marginals. So if you want to know if the edge, given your sentence, what is the probability of that, you just need the beliefs. Because after convergence of this message passing, either going for these message passing, after it has converged, then what you need is your beliefs. Because beliefs are related to your marginals. You need these beliefs in order to calculate the marginals. Because why do we need marginals? As I said, because it characterizes, it distinguishes different parses. So everything is quite clear. And P3 factor is our challenge. As I said, it is the hardest constraint. That's why we call it hard constraint. No, it is hard because we need to prove that your graph, this is the factor graph. It's a different story. We need to make sure that our dependencies, they don't create a loop, because we can assign any number, because after all it's just linear programming. If we don't provide enough constraints, then it can create lots of nodes, and it can create some loops, and we don't want loops in a tree. So it's our challenge. We aim to find the parameters and minimize the regularized, this is regularization, the regularized objective function over the training samples, sentence and the parse. And so we locally minimize this objective using autogradients, but with composite mirror descent algorithm. And it's a variant of stochastic gradient descent that uses mini batches. And so it's just a technical things. Let's skip that. Our objective function, as I said, the standard choice for J is just the negative conditional likelihood. However, our aim is to minimize expected loss on a true data distribution. Over this, since the true distribution is unknown, we substitute the expected loss over the training sample and regularize our objective in order to reduce sampling variance. Specifically, we aim to minimize the regularized empirical risk with J set to L, and this would not be differentiable. So let's calculate the gradients. We apply, as I said, automatic differentiation, AD, in the reverse mode. This yields the same type of backpropagation that has long been used for training neural networks. So you see, this automatic differentiation is just like a miracle. And inference and decoding loss, so everything is in this block. It's a feed-forward topology of an inference. First, we compute the potential using that log linear model. We initial messages, because first, in any message passing, you set them to 1. Then, you messages at time t, you update them up until convergence, and finally after convergence you get the beliefs, and beliefs are those marginals that you need. After that you can compute J is equal to minus that likelihood that I said, so I use this for this probability, and we get our decode. We update the parameters to have a lower loss until it converges. So our true loss by way of decoder contains argmax over trees and is therefore not differentiable. But we show how to soften this decoder by substituting a softmax, making it differentiable. And empirically, we find the above objective difficult to optimize. To address this, we substitute a simpler L2 loss function, and we will show how to run backpropagation through the inside-outside algorithm on hypergraphs. By the way, I have explained inside-outside algorithm on one of my lectures on probabilistic context-free grammar. Differentiable loss function. So we redefine J to be a new differentiable loss function. So let's call it the annealed risk, which approaches your loss when your temperature goes to 0, because it has a temperature variable. If it goes to 0, it approaches you with the loss that we have. So if you are familiar with simulated annealing, so those temperature variables arise in those models, which is a very classical idea in artificial intelligence maybe 20 years ago. And so our Q is proportional to expectation of the probability that an edge exists. And we sum over all edges that exist in that parse, so we get Q. And to compute the annealed risk, observe that it simplifies to this one. So this is a negated expected recall that I said. Expected recall of a parse, let's say. And we obtain the required marginals from this equation. And of course, these are really important. As I said, the gap between belief propagation and backpropagation is important. So this article says by Eaton, he has a thesis on that belief propagation generalizes backpropagation. In 2022, he has very few articles, but all of his articles are fantastic. For example, this article is fantastic.